Hello everyone. Mr. Shang just introduced the strategic direction and scenario-based solutions of Huawei mass storage. Today, I'd like to share with you the design and details of the architecture. Since our first storage product for mass data launched in 2009, we have continuously improved product performance. Up to now, we've created 3 generations of mass storage. The first generation adopted the shared everything architecture to create the first storage for mass data in China and achieved high-performance service sharing. In 2014, we launched the first enterprise-class distributed block storage with the shared nothing architecture, providing users with high scalability and support for multiple services such as files, objects, and HDFS. In 5G and AI era, explosive data growths will make conventional storage obsolete, and users will need storage offering high reliability, data interworking, and high-performance processing. To tackle these challenges, we have broken the boundaries of architecture, service, and performance, and redefined mass storage. To this end, the next generation of future-oriented storage for mass data was born. It implements on-demand expansion of storage and computing power based on the composable infrastructure architecture. Now, let's see how it works. Traditional data storage adopts either shared everything or shared nothing architecture. Shared everything supports flexible configuration in small capacity scenarios, whereby if a node fails, the corresponding node will take over the services. But this architecture has limited scalability. Shared nothing architecture provides higher scalability, but it needs to deploy multiple nodes at the beginning, leading to high cost of data reconstruction in the event that nodes fail. To solve this problem, we decide to combine the advantages of shared everything and shared nothing into one revolutionary architecture. Therefore, we divide each physical node into multiple V-nodes. The multi-level views and data layout technology helps achieve physical node and V-node security. Traditional mass storage can only tolerate one physical node failure when the number of nodes are limited. Our new architecture can tolerate the failure of 50% nodes without data reconstruction, greatly improving reliability. In addition, when nodes increase, V-nodes support automatic data balancing and can tolerate the failure of multiple nodes. Another important technology of our new architecture is elastic EC. We combine high-ratio EC and V-node architecture to provide over 92% storage utilization when at least 2 controller enclosures are configured. In addition, the LDEC algorithm improves the reconstruction efficiency by 30%, and the unique incremental EC technology improves storage performance and system reliability. A traditional storage system can provide only 1 or 2 types of services. For example, some converged storages may provide SAN and NAS services. However, data is increasingly diverse, and different applications need to access the same data through different interfaces, including files, objects, and HDFS. This requires data convergence and interworking. That reminds me of data lakes. Data collision and retrieval unleash the value of diversified data. As the foundation of data lakes, mass storage must support uncompromised interworking of unstructured data. In this way, one copy of data can be accessed through different interfaces such as files, objects, and HDFS without data migration or semantic or performance loss. Our achievements lie on the basis of 3 innovations. The first one is service convergence. The multi-mode adaptation technology helps converge the metadata of the 3 services and form the Unified Distributed Relational Object Service, or DROS. Our products also support multiple models in one converged storage pool. This storage pool supports diversified data stripes and provides space allocation interfaces with different granularities for the service layer. meeting differentiated requirements of multiple services. The last is Quality of Service Technology, or QoS. Based on CPU core scheduling, we implement end-to-end QoS guarantee for transaction-based services, which combined with burst control, help ensure the quality of different services. One traditional storage can provide either ultimate bandwidth or optimal OPS. Therefore, users have to use different storage devices in different phases of data processing, which reduces the overall efficiency and increases costs. Therefore, the main challenges for us are metadata management conflicts caused by large and small files, and I/O mode conflicts caused by large and small I/Os. To address these problems, we take 3 measures. The first measure is about data layout, such as affinity distribution for metadata. By processing metadata with ownerships, we slash performance overheads caused by distributed locks. In addition, we achieve adaptive space allocation based on different I/O models, resolving metadata management conflicts caused by large and small files. Next, the I/O modes are adaptive. For example, large I/O writes run-in pass-through mode, small I/O writes run-in aggregation mode, and large block data reads use the triangle mode to reduce bandwidth consumption. Multi-level intelligent cache and battery-protected memory help us prevent I/O mode conflicts caused by large and small I/Os, while also improving performance. We offer optimal convergence of services by breaking the 3 boundaries. We provide users with efficient storage in mass data and multi-service scenarios, reducing end-to-end TCO. However, as QLC and NVMe over Fabrics technologies mature, media and computing power are not matched in terms of performance and lifespan. Therefore, we needed to find a way to flexibly configure storage and computing power. We plan to adopt the composable infrastructure architecture to address this challenge. Our mass storage will evolve into 3 compute components, including edge, performance, and compute models, and 2 storage components, including high-density SSD and HDD enclosures. Together, these 5 components support Lego-style assembly, implementing flexible configuration of storage space and computing power services for diverse service scenarios. We also implement interconnection and elastic expansion of these 5 components through memory fabric and plug fabric. On storage layer, based on Huawei-developed plug fabric interfaces, we provide globally shared storage semantics with high speed and pass-through performance, eliminating the limits of media and nodes and restrictions on premises and in the cloud. At the compute layer, we use Huawei-developed memory fabric interfaces to implement high-speed interconnection of memory-level media among nodes. We also provide global memory semantics to support evolution of new technologies, such as memory or stream applications. In addition, we have also built intelligent storage devices to bring compute and storage resources, and created the computable storage. The storage devices have compute capabilities that meet the needs of data-centric architecture. We also use Stream Smart Disks to eliminate space management and provide advanced stream interfaces for simplified storage systems and high performance. The IP Smart Disk enclosure supports in-storage computing for nearby data processing, reducing network bandwidth and improving performance by several times. Last year, Huawei set up the Olympus Award to encourage scientific researchers to tackle technical difficulties. Named after Olympus Mons, the highest mountain in the solar system, it is the latest step on our quest for technological innovation. Our storage team continued to further progress and conquer Olympus Mons, building the trusted choice for mass data. That brings me to the end of my speech. Now let's invite Mr. Chen San, our hardware architect, to the stage, who will introduce the high-density and large-capacity Pacific series of OceanStor storage.